So, hi everyone. I would like to welcome you at today's Extreme-Len Probabilistic Combinatorics webinar. And today, today's speaker is Jan Hladky from Czech Academy of Sciences, and he's gonna talk about flip processes on graphs and dynamical systems they induce on graphons. Okay, so and just one more thing before I hand the token to the other Jan. If you have any questions during the talk, write it to the chat, and either Jan himself will see it, or if not, I will try to let him know about the question and he will address it. Okay, so Jan, the virtual stage is yours.
Okay, so thank you, Jan, and thanks everybody for coming. I will talk about a certain class of processes on random graphs, and we were looking at it with Frederick Garbe, who was a postdoc here at the Czech Academy of Sciences, my colleague Matas Šileikis, and Fiona Skerman from Uppsala. So what I would like to do is first give you two examples, or set up the things so that two well-known processes fit in this class of flip processes, and these are the Erdos-Renyi random graph process and the triangle removal process. Okay, so let me recall this GNP. That's what's called the binomial Erdos-Renyi random graph. You have n many vertices. They are labeled with integers 1 to n, and you have a real parameter p between 0 and 1, and you should think of as fixed. So we will be working in this dense regime, and that's the p is the connection or the probability of each pair becoming an edge. Okay, there is a related model which is called the uniform Erdos-Renyi random graph. The second parameter, this parameter m, is an integer, any integer between 0 and n choose 2, and that is in that model among all n-vertex graphs, again on your vertex set labeled 1 to n, you pick one graph among those that have exactly as many edges uniformly at random. Okay, and for my purpose, or for the purpose of this talk, when m equals p times n choose 2, these models will not be any different. So again, these two models are not the same. For example, because the latter model always has the same number of edges, whereas in the former model, you have fluctuations in the number of edges. But for the questions I will be dealing with, these two models are indistinguishable. Okay, and often when you are looking at the uniform Erdos-Renyi random graph, then there is a sort of a finer point of view you may want to have, and that is not to look at one snapshot at one random graph, but rather at an evolution. And this is called the Erdos-Renyi random graph process. So what you have here is you have your vertex set, and then you start with the edgeless graph. So that's G naught on your fixed vertex set. That will be always n vertices labeled 1 to n. And then in each step, you pick in the previous graph. So if you want to obtain GR plus 1 from GR, then in GR, you pick one non-edge uniformly at random, and you turn it into an edge. Okay, so naturally, this process can't proceed any further than n choose too many steps, because at that moment, you necessarily turned every non-edge into an edge, and there is no way to continue. Okay, so that's how this process is defined. Okay, and so what's a well-known fact is that with high probability, everything on this slide is quasi-random. Okay, I will recall this notion of quasi-randomness with high probability as n goes to infinity. I will have this definition of quasi-randomness on the next slide. But for example, with this Erdos-Renyi random graph process, the way you should read it is that for every fixed epsilon, throughout the evolution, all these graphs G1, G0, G1, G2, G3, they are epsilon quasi-random graphs, of course, with increasing density. Okay. So let me try to give you this definition of epsilon quasi-randomness, at least very briefly. You have this notion of density, which is just the proportion of edges that are in your graph relative to the number of all possible edges you could have. And then you say that a graph is epsilon quasi-random if this density is essentially inherited to every subset, or at least every subset of substantial size. Okay, so if every set of vertices induces a graph of a similar density. Okay, so here is an example. I believe that these people have seen this, so I'm just going very quickly through this stuff. This is an example of a very non-quasi-random graph, so it would probably fail to be quasi-random even for epsilon equals maybe 1/2 or 1/4. You have this, say, complete balanced bipartite graph, and if you take U to be this set, then the vertices induced by this set U induce 0 edges, which is a density very different from the overall density of the graph, which is 1/2. Okay, so this is a notion I will work with. Okay, so we saw one probably the easiest process to define, this Erdos-Renyi random graph process, in which you were sequentially turning non-edges into edges. So let me recall one other well-studied process, which is called the triangle removal process, that was introduced in the 90s by Bolobash and Erdos, and has been a subject of immense research since. So this time, let's start with an n-vertex clique. Okay, you could switch into complement and start with an independent set if you wanted, but that's the standard setting. You start with a clique, and what you do to get a new graph from a previous graph in this process. So again, you go one by one. You pick a random triple of vertices, but you condition that triple to induce a triangle. Okay, and you delete the 3 edges of the triangle. So you never touch the vertex sets, but you pick a uniformly random triangle in the graph you have, and the new graph is formed by deleting the 3 edges. Okay, and so the state of the art in this process, okay, so now, unlike in the Erdos-Renyi random graph process, it's not clear when do you actually stop. So obviously you stop when there are no triangles left, because then the process is not defined. But this is a random time which depends on the actual choices of deletions you made in the process. And the state of the art here is a result of Bowman, Fries, and Lubetzky, which tells you that you stop at time, so that no triangles remain at the point where there are something like n to the 3/2 many edges left. Okay, so that's you need to do very delicate analysis for this, but from a, sort of conceptually what you need to prove a certain the quasi-randomness of the evolution. Okay, so what if I have these sort of glasses of dense graph theory? So if I don't care about edits of subquadratic number of edges, which is what is my setting throughout this talk, then what I would say is that you end up with a graph which is essentially empty, and throughout this evolution you remain epsilon quasi-random for an arbitrary fixed epsilon. Okay, so again, this is, this was something that was known already in the 90s. This is by far not a very weak variant of this result of Bowman, Fries, and Lubetzky. Okay, so we saw these 2 graph processes, the Erdos-Renyi random graph process and the triangle removal process. So let me quickly change the setting somewhat so that it fits better into this setting of this newly introduced class of free processes. And so that's what I would call the Erdos-Renyi flip process. Okay. So now let's start with a graph again, as in the Erdos-Renyi random graph process. And you can think of the edgeless graph again. And in each step, what you do, you will pick a uniformly chosen pair and replace it with an edge. Okay, so the difference here being that you are not necessarily picking a non-edge, but you can either choose an edge or a pair. So there is no conditioning there. Okay. So let's quickly, so we saw in the Erdos-Renyi random graph process, we knew that after L many steps, we have exactly L edges in. So let's quickly calculate how many edges, what is the density in this modification when you, after R steps, okay? And the rescaling I want to do here is let R be alpha times n square, where alpha is a constant. Okay, so that's of course a very quick calculation because the density of a graph is the same as a probability. All the pairs are the same, that it's completely symmetric. So probability of any fixed pair, let's say U and V, being an edge, that's just 1 minus that pair being a non-edge. And for that pair to be a non-edge, it couldn't have been touched in any of these R many steps, right? So that's the calculation you have here and some approximation by the exponential. Okay, so we see that after alpha times n square many steps, the density is 1 minus the exponential of minus 2 alpha. Okay, and so here is the plot. So the way you can read it is that maybe at time 1.2 times n square, the density of the graph is around 90%. Okay, of course, you can easily show that this random variable, the density is concentrated. So okay, so that was the modification, this flip process, the modification there being that we considered or sampled all pairs. Okay, let me quickly mention a variant which I could call a 50-50 flip process. And what I would do there is I would not replace with an edge, but I would replace with either an edge or an non-edge, depending on an outcome of my fair flip coin. Okay, so I hope this modification is clear. And what I would say in this setting is that, so, once you pick a pair, it becomes sort of a quantum pair, right? So it's 50-50 edge or a non-edge. And what I would say in this setting is that this process converges to a quasi-random graph of density 0.5. So maybe let me explain what I don't want to explain formally what it means, but maybe rather let me explain what it does not mean. Okay, so at any time t, it might happen that between this time t and time t plus n choose 2, your selection go over one by one over all pairs of your graph, of your host graph. And in each of these selections, you switch the corresponding pair on, right? At each point, this event of somehow in the next immediate n choose too many steps, you switch everything on, that happens with positive probability. So in particular, if you run this process forever, then infinitely many times your process, there will be states when your process is a clique, and by symmetry, there will be states when your process is an independent set or edgeless graph. But that's not what I mean by this, because if you know, there is an easy calculation that the first time this very exceptional event happens is maybe exponential in n to the 4 or something. And that's somehow beyond where I am looking. I'm only looking at times which are of the form c times n square. Okay. So I will have a certain class of processes and I will be tracking them for times which are of the form c times n square, where c is any real number. I will not be looking what happens at time which are exponential in n or exponential in n to the 4. Okay, so now let me insert the word flip into the triangular removal process. And the idea is again the same. You start with a graph, and again, you may think of the complete graph, and you pick a triple of vertices, but you don't condition them on forming a triangle. You just pick a uniformly random triple of vertices, and how you define your next graph in your sequence is, well, if the triple didn't induce a triangle, then you just copy the graph. And if it did induce a triangle, then you remove the 3 edges. Okay, so note that this is exactly the usual triangle removal process, except that it's sort of slowed down at random times. But the sequence of triangle removals has exactly the same distribution. One advantage of this is that you never get stuck, right? Even you can run this process forever, even if you have a triangle-free graph, say, to begin with. Okay. So let me quickly argue how the density, how the number of edges evolves throughout the run of the graph. So again, I want to understand how many edges there are in GR, where R is a constant times a given constant alpha times n square. Okay, and a little warning, even though somehow we are working with triples of vertices, still there is quadratic scaling. So we will always have, on the time scale, we will always have quadratic scaling. This has to do with when you want to track edges, like what happens to the edges of the graph, and there are quadratically many of them. Okay, so these are, I have these two variables, which random variables, which are really the same thing except rescaled. I have the density at time alpha, and the number of edges at time alpha, and the density at time alpha. Okay, and what I know, no matter what the density at time alpha is, if it's some number d of alpha, then I know that the probability that 3 vertices induce a triangle is d cubed. So here I'm borrowing this result of Bowman, Fries, and Lubetzky, or any other of these previous quasi-randomness results, because I know that I have a quasi-random graph, right? So what does it mean? How does the between time alpha and alpha plus epsilon, everything under quadratic rescaling, how many edges are deleted? Well, in each deletion, I always, you can see the pointer, right? The mouse pointer. Yes. So in each step, when I delete something, I delete exactly 3 edges. Well, then I'm looking at a window of length epsilon n square. So that's the length of the window. And then what I argued that in each step, individually, the probability of actually performing a deletion is d cubed, right? So the only slight cheating here is that I didn't specify whether this is d cubed of alpha or alpha plus epsilon, or it's alpha of something between 0 and epsilon. But that's sort of okay if epsilon is small, right? So, and that of course leads, like if you rewrite this, that leads to this differential equation. Aha. So where the 2d's in the numerator and the denominator are different, right? So this is the change of function d alpha with respect, and this is this derivative notation d of alpha. Okay, so that's a differential equation in.
So there is like one more d missing, right, in the numerator.
Well, I think this you should just, this should be with a different font, right? It's d alpha with respect, derivative taken with respect to alpha. Yeah. And yeah, so that's, so, and then you rewrite the right hand side. So this is the same equation, just rewritten in the infinitesimal notation. Okay. And okay, and then of course, when these days people don't solve differential equations, they just open Wolfram Alpha and plug it in. And the initial condition was d0 equals 1, right? Because we started off with a complete graph. And this is the plot you would get. Okay, so you have sort of a much slower convergence, but convergence with the density as to 0. So maybe a remark, a trivial remark, which I want to make, because then we will be using something similar in a more complicated setting. If you don't know how to solve a differential equation, given of this type that's called a separable first order ordinary differential equation, then what you might do, how you would sort of numerically plot this is, well, you know the initial condition, d0 equals 1, and hence you can calculate the right-hand side of this, right? And then you can linearly, plot a little linear piece of the initial evolution of your, your d up to time epsilon. And then you get a new estimate for your value of d at some time epsilon. You again plug it into the right-hand side, and this way you can iterate. Okay, so that's the differential equation is this simple that you can very easily numerically do this. Okay, so at this moment we saw two particular examples of what we will call flip processes. So I think on the next slide I have a general definition. So this is what I would call a flip process of order k. Okay, and I have an example, k equals 3. So what this is, it's a rule. It's just it's a rule R. This rule R is just a table, and the table on the left-hand side, it has all possible labeled graphs on k many vertices. So here on this table there are 8 possible graphs, or 8 possible labeled graphs on 3 vertices. So they all appear on the left-hand sides of the entries of my table. Okay, and the way this flip process works is you start with your favorite large n-vertex graph. So that's G naught. And then in one step, you sample k vertices in your large. You sample a random k tuple, and it induces a certain graph on k vertices. And you look up in the table what that graph is. And then you have the rule. So what is to the right of the pink arrow, it tells you what you should replace the sampled graph with.
So Honza, do you assume that you have an ordering of the verts in G0, right?
Yes, I will first sample vertex which I call 1, and then I will sample a vertex which I call 2, and then I will sample a vertex which I call 3. Yes.
Okay.
And the graph is large, so you don't have to worry much about one vertex being sampled twice. Okay, so that's a event that happens with a small probability. If it does, maybe you resample or something. Okay, and by the way, as in this Erdos-Renyi 50-50 flip process, I may have randomized entries. So for example, if my induced subgraph, if my induced triple happens to induce this, there is an edge on 2-3 and an edge on 3-1, then what this entry tells me is that I should flip a coin, and with probability 50%, I will erase the 2 edges, whereas with probability 50%, I should insert the edge 1, 2. Okay, so there is this you might call the restricted class, when on the right hand side you don't have any randomization. I don't know, non-randomized rules, and then this would be sort of a rule with randomization. Okay, so that's I think a very general class of random graph processes. You just fix a k, you come up with a rule, and no matter what starting graph you have, you can run this process forever. It's well defined for arbitrarily many steps. Okay, so let me quickly give you some examples of processes which fall into this category. One would be what we call ignorant flip processes. And so what this subclass would be, these are processes where the right-hand sides of your table, so the thing you see right of the pink arrows, would be independent of what you sample, right? I will sample, let's say, a quadruple of vertices, and then no matter what I saw, I will just insert a 4-cycle 1, 2, 3, 4, right? So both the Erdos-Renyi and the Erdos-Renyi 50-50 processes, they were of this type. Erdos-Renyi flip process and the Erdos-Renyi 50-50 flip process. In both of these cases, it didn't matter whether you sampled an edge or a non-edge. Okay, so what's next? Removal flip processes. This is obvious. You can generalize from removing triangles to removing any other structure. So what you have, so complement flip process, that would be just you sample something, you sample 4 vertices, and then what you insert instead of this induced subgraph would be exactly the complement, the graph complement. So edges become non-edges and non-edges become edges. Okay, so that's again another process. What you might have is, I have a picture here, this component completion process. So here on this picture, you would, maybe I have a component, I have the component completion flip process of order 6. So I would be sampling a 6 tuple of vertices. It would induce something, and then I would replace it with what's called a component closure, right? So I would add so many edges not to merge any components. Okay, so maybe let me sort of give you one word or one sentence answers to what can you say about these processes. Say, for example, with these flip processes, what you can say is no matter what graph you start with, you will converge to a quasi-random graph. Okay, with a density you can calculate just from the output distribution. With the complement flip process of any order converges to a quasi-random graph of density 1/2. The component completion process, this I think this is clear. No matter, you start with a graph, and the process eventually reaches what's called the component closure of that graph. So any initial component just becomes a clique, and no 2 components get merged. Okay, so maybe one more example I want to explain quickly is you might have what we call a stirring flip process. So what you would do, you would sample maybe a quadruple of vertices, and a quadruple of vertices can induce any number of edges between 0 and 4, choose 2. And sort of your rule would be, well, you know, replace. So if it induces L many edges, then replace the induced quadruple, the quadruple, with the uniform Erdos-Renyi random graph on 4 vertices and L many edges. Right? In other words, just preserve the number of edges, but otherwise sort of try to get rid of the structure as much as you can. Okay, so obviously in this process, you don't change the number of edges at any step, but you are losing the structure. So you would converge, given an arbitrary graph, you would converge to a quasi-random graph of the same density as the original one. Okay, so what we can do is, in some sense, we can describe the behavior of each such process with each, with respect to any given initial graph. We use the theory of Graphons to that. So let me quickly recall the definitions. I don't have time to go into detail. So Graphons are symmetric functions defined on the unit square with values in the interval 0 and 1. Okay, and they are meant to represent limits of large graphs, or approximately represent every large graph, if you will. And the way one should think of them is some version of the adjacency matrix of that graph looked at from far away, right? So if you have a graph, okay, and the vertices of that graph are labeled with integers. So it's as on this example, I have a finite graph, then you can write down the adjacency matrix with rows and columns following the labels on your graph. And then what you do, you just squeeze your adjacency matrix into the unit square. So the entries in these examples would be little squares of measure 1/16. Okay, and what I'm using this is what I mean by this picture. I have the 0, 0 corner here, the 1, 1 corner here, and white represents the values 0 and black represents values 1. So in this adjacency matrix representation of a graph as a graphon, you don't ever use any values strictly between 0 and 1. You only use zeros and 1s. On the other hand, if you have a really large graph, like on this picture, I have a graph which consists of 2 blobs. One blob is labeled with integers from 1 to 0.3n, and this part doesn't induce any edge. And then I have remaining vertices. They are labeled with integers from 0.3n plus 1 up to n. And they induce a quasi-random graph of density 0.8. And what is between the blobs, there is, well, what you might say is an epsilon regular. So it's a regular pair in the sense of Semeredis regularity lemma of density 0.4. Right? Then the whole point of this theory of graphons is that maybe you don't want to you don't want to write down the entire adjacency matrix entry by entry, but in that setting, you can approximately capture that with a graphon in which there is an interval of length 0.3 followed by an interval of length 0.7, and in the four parts of the graphon, you just capture these densities. So the density 0 corresponding to the inner density of the first blob is in this top left corner. The value 0.8 is in the bottom right corner. That corresponds to the inner density of the second blob. And this density of 0.4 that represents, well, the cross connection. Okay, so that's, and there is this cut norm, which I will not define, but it allows you to measure how far 2 graphs are apart in some suitable sense. And also it allows to compare distances between graphons. So primarily it's defined on graphons, but then through this embedding, it's also defined on graphs. Okay. So now let me try to explain the relation between these flip processes, which were sort of a very, I think, easy to define combinatorial things, and graph limits. So what we do is we construct trajectories. So what is a trajectory? Well, formally, it's just a function defined. So you feed in 2 things. One is a graphon. So I write this calligraphic W node for the set of graphons. You feed in a graphon and a real parameter, non-negative real, and this trajectory outputs a graphon. And and the notation, by the way, we don't write it as a 2-variable function, but we put the graphon, the first coordinate, into the brackets, whereas the second coordinate goes as a subscript. And the way you should read it is that this is the value, so phi tw is the value of the trajectory, is the position of the trajectory given an initial graphon w and time t. Okay, so in particular, when t equals 0, phi tw equals w. Okay, and I will later show you, or at least hint how to construct these. And on the next slide, I will try to say what these trajectories are good for. Okay, so far this was just a definition, or not even a definition. That was just an introduction of a function phi. So, and the main point is the following transference theorem. So you give me a rule. Okay, so again, a rule is just a table for, you have a certain order, and the table has 2 to the k, choose too many entries, and tells you how to do the replacements. Then we can construct trajectories in a way so that whenever you give me a graph G0 and it's large, and you perform this flip process for R many steps, where R is some constant times n square, then with high probability, okay, and I'm being loose here with quantification here, then with high probability, you will end up close in the cut norm to the trajectory at time t started from any graphon that was close to your graph G0. Okay, so maybe let me try to read it or explain it again. I'm comparing these two. I'm comparing two objects. One is a deterministic and so analytically defined, so analytic trajectory, right? And another is a discrete and random process, right? Which starts at a graph G0. This G0 is a finite graph, but through this embedding, through this adjacency matrix representation, I can view it as a member of my graphon space. And then I have, I have this discrete evolution of my process. It's a discrete random evolution. That's what these dots are. And then what I'm saying is that GR in the cut norm is close to phi t of u, where there is this rescaling, which basically tells you that, graphons don't know any n. Graphons don't have a particular number of vertices, so you somehow need to get rid of it. Okay. So that's in some sense the theory that the theorem that makes the whole theory reasonable. So if there are any questions, then I am happy to answer them. Okay, if not, then let me, okay, I will then talk a little bit more about what you can get from this theory, but let me just make a sort of small remark here that, let me say it in a way that doesn't refer, which doesn't need your expertise in graph limits. So suppose I have this input graph G, and that may represent, let's say, you have some sports union or something, and you have insert many football players, and you have insert many cyclists, and you have insert many long distance runners. And maybe, and within each of these three groups, you have these quasi-random connections of the densities as indicated on this picture. And you also have densities across, so like friendships across, right? So, and again, they are quasi-random. Okay, and then you have some dynamics, right? So these athletes meet in some random quadruples, and they update their friendships after each meeting. And maybe after 100 n square steps, you end up with, your new friendship graph like shown on the picture, right? So you have again three blobs with quasi-random connections between the pairs of blobs and inside the individual blobs. But then, of course, somehow you still want to know, okay, but which of the blobs were the cyclists, which of the blobs were the football players, right? So if you want to talk graph limits now, then yes, we do keep track of the order. So in other words, we do talk about the cut norm and not about the cut distance. We don't mod out, as is maybe more usual if you want to get compactness of the graphon space or something. Okay, so our results would actually tell you, or our trajectories would tell you which of the three blobs are the football players, which of the three blobs are the cyclists. Okay, so now, so what we did so far, I claimed that we can, given a certain rule, given a certain flip process, I can, starting from any initial graphon, I can construct these trajectories, which will predict how my flip process, finite flip process, will behave. So now I want to show how you do it, how you construct these trajectories. So the setting is, okay, and I will be, there is the formula we have in the paper is sort of messy, but I want to show you the idea on the case of the triangle removal flip process. Okay, so I want to deduce a formula for trajectories or some description of the trajectories for the case of the triangle removal process. So you give me a graph on U, and you ask me how does the trajectory evolve. And the thing is, we don't really construct the entire trajectory for every time. This is a little bit like the solution, this numerical solution to the differential equation. It's sort of enough to construct the trajectory only for the next time, for the following time epsilon. Because if you can do that for every graphon, then you will just first construct your epsilon length of your trajectory, well, and then repeat the construction from that point on. Okay. So I'm now focused only on constructing an initial segment from graphon epsilon, an initial segment. So this is what I want to understand. What is the change at any value xy, because understanding a function is nothing else than understanding the function at any point. What is the difference between u and the trajectory of u at 4 times epsilon? Epsilon is small. Okay, so here's the picture. This is the point. This is the change of the point you want to understand. Well, and now you just remember what this is all supposed to represent, right? The graphon is supposed to represent a graph, and the value xy in that graphon is supposed to represent two infinitesimally small sets of vertices, let's say x and y. Okay, and maybe this infinitesimal parameter here is called gamma. Okay, and in that graph, I want to understand the evolution of the triangle removal process for the next epsilon n square many steps, because I have the rescaling, between the analytic object and the finite object. Okay, so the change of the value of the graphon at position xy corresponds to, well, additions or deletions. We actually know that in the triangle triangle removal process, there will be only deletions in the pair xy, right? So this pair, it formed, there was some density of this pair, and now I want to understand how much it goes down. Okay, so let's do it. So what is, so I have, in this graph, I'm performing epsilon n square many steps, and an edge gets deleted inside this pair only when one of the sampled vertices, of the 3 sampled vertices, falls into the set X. Well, that's probability gamma. Then I also need another sampled vertex to fall into the set Y. That's another factor gamma, right? Because Y spans only a gamma proportion of the whole graph. And then I need an expression or a parameter which tells me, well, what is the density, what is the probability of 3 sampled vertices, one of them conditioned to land in X, another conditioned to land in Y, and the third, taken from the entire graph G, what is the probability to form a triangle? Well, and that probability has a name in the theory of graph limits. If you sort of transfer it back to the graphon, it's this two-rooted density of K3 in U, where the roots are at X and Y. There is a simple integral formula. So in expectation, the number of edges you remove between X and Y is this much approximately. And hence, yeah.
I'm sorry, should it be scaled by 3? Because
yeah, I guess, right. So I know that I said, well, there is a difference between saying one of the vertices has to land in X and saying the first vertex has to land in X. So yes, there is a difference of 3 or 2 or 6. Yes. Sorry. So the density change, within time epsilon can be described using this two-rooted density. Okay, so let me sort of say basically the same thing again. So what we do is inside the set of graphons, inside the universe of graphons, we construct what is a counterpart to derivatives for real functions, but now I'm not doing derivatives of real functions because my trajectories are not real functions, they are graphon valued functions, right? And we call them velocities. So the velocity is that it's the same formula as for derivative. You just take the difference of the evolution of your sought after trajectory at time epsilon, and so the difference to your graphon, you divide by epsilon. That would be the velocity at the graphon, that you construct given error. And on the last slide, and once you have that, then you can, of course, again, just going a little bit with the direction you linearize, you go a little bit in the direction of the velocity, and then you follow the new velocity. And this way you can construct the entire trajectory. So I hope on the last slide, I calculated the velocity for the triangle removal process. Okay, so this is just the expansion of this two-rooted density of the triangle. Okay, and you can do that for any rule. Okay, so oops. Okay, so I hope that in some sense I conveyed this idea that you can indeed, with a bit more messier formulae, but you can construct in some fairly explicit way these trajectories for any flip process. So maybe let me now try to address this question: what is this all good for? Like, I have this transference theorem, and based on that, I could, for a particular graph process or flip process of interest, I could probably calculate the trajectories in some way, and I could tell you how your graph will evolve, maybe starting from the empty graph, from the complete balanced bipartite graph. There are many things you may consider as your initial graph. But you probably could do all that by hand, writing down some system of differential equations. So what I want to do in this remaining 5 or 10 minutes is to convince you that there are properties we can deduce in this graphon setting, which would be difficult to formalize without using the notion of graphons. Okay, so that's maybe the same argument you may have with graph limits in general, that many things where graph limits were used, you might do just with the regularity lemma or something, but then there are some concepts which become much easier to be treated when you switch to this graphon language. Okay, so let me maybe let me maybe explain one property which we could obtain in this setting. And that is that these trajectories don't ever merge. Okay, so confluence, so what I had to learn for this project, that's when two rivers meet. Okay, so that doesn't happen. So what we prove is that when you start with two different graphons, then the trajectories don't ever collide. Okay, there are many, and there are similar statements. There are similar statements that that you can make, and maybe I will get to some of them. Okay, so let me try to explain this theorem. If it's clear, then let me try to explain this one now. Okay, so I claim that whenever you have a rule and you have two graphons, x and y, then what can happen? Well, either x lies on the trajectory of y, so you have sort of a trivial, you know, that's not really a confluence, right? Or y lies on the trajectory of x. Or if it's not the case, then the two trajectories don't ever meet. Okay. So that's a theorem we want to prove. Okay, and I don't want to talk, or the way I think of it as is not as graphons, but rather as car crashes, right? So I want to prove that I have some sort of conditions that two cars don't crash. And by the way, you know, for cars, cars don't only crash, or trajectories of two cars intersecting is not a sufficient condition for, you know, a car crash occurring, because it only also has to occur at the same time, right? You not only have two cars have to be at the same position, but also at the same time. But it's enough to only prove that these car crashes don't occur, because if two trajectories you know, would go through the same location but at different times, then you would just, you know, start one of these trajectories a bit later on, and then you would have a crash really at the same time. Okay, so what I want to prove is that when you have two different graphons, x and y, then for each t positive, for each positive time, the trajectory of y at time t is different, or the position is different than the position of x at time t. Okay, so now let's again switch to car accidents. So there are, what you want to prove that you know, a car accident will not occur within the next second. That's the only thing you need to prove, and you want to prove it for every second. Then you are fine, right? You don't want to do it for 1 hour ahead, because yeah. So when do I have a guarantee that two cars don't crash? Well, one thing is that when two cars are sufficiently far away, right? If two cars are a kilometer away, they don't crash in the next second, and I don't have to worry about anything. But that's not the only setting. Then another setting is that two cars are close to each other, and that is also fine if their velocity vector is almost the same, right? That's what happens in packed cities or on packed streets all the times, that, you know, cars are very close to each other, but their velocity vector is almost the same. So here is the proof then. So you have these two, well, x and y, the two graphons, and you introduce this variable you want to track, which is just the distance of the corresponding trajectories at any time t. And you want to, the only thing you need to prove is that this, if ht was positive initially, it remains positive throughout the evolution. Well, but then what you can do is you prove that the velocity, the difference of the velocities is just a constant, is upper bounded by a constant multiple of the distance between the graphons themselves. Okay, So in other words, if the two cars are close, then their velocity vectors are necessarily almost the same, and then a crash can't occur. Okay, so that's, you know, it leads to this differential inequality, and that proves, you know, so a solution to this differential inequality tells you that if initially you had positive distance, then you remain positive all the time. Okay, so, you know, that was one example of something which I think would be difficult to formalize for finite graphs, right? So if you have two graphs, maybe with a different number, initial different number of 5 cycles, for example, substantially different, then you know then that running the two flip processes, starting from either of them, you will never arrive to the same structure. Right? That's what this theorem tells you. Okay. And now, in this last 3 minutes, I want to maybe explain what there are many open problems here. So I will indicate maybe one line of possible research. So suppose you have a rule R, and you have this trajectory. And what we saw already is that in many cases, the trajectory converges, it converges, okay? So for example, if you remember these ignorant processes, then the trajectory, every trajectory would converge to a constant, converge rather quickly to a constant graphon, right? Because I previously said that it converges to a quasi-random graph that translates to convergence to a constant graphon. Okay, so this word typically, I don't mean in any mathematically precise sense. We have an example of a trajectory which is periodic. So you start with a certain structure, you go to a different structure, and then you return back. So you are circling, you are in a cycle. We don't understand these trajectories that much more. I mean, there are of course zillions of questions people study in dynamical systems, some stability questions and so on. So let me give you one which, in my opinion, I quite like it, and in my opinion, it really justifies this language of graphons. Okay, so you start with an initial graphon X, and you consider the trajectory. Now I sort of forget about time. I just look at the line, look at the curve. And remember, we are working in these cut norms. So it's the space of graphons equipped with the cut norm rather than the cut distance. Okay, so this is a non-compact space. It's a huge space. So my question is, can the trajectory be really complicated? Can it be totally unbounded? Okay, so if you take this set T and you take its closure, then could you get a non-compact subset of the space? Okay, so that's one question, and of course there are many other which you may want to ask, and we can answer some, we can't answer many others. So with that, let me thank you and stop now.
Thank you, Jan, for a very nice talk. And I ask everyone who wants to unmute themselves I ask everyone to unmute themselves and give a round of applause to Jan. So are there any questions? Actually, I do have a one. So I understand why the scaling, why the time scaling by n square was sort of natural with respect to the triangle removal and just the Erdos-Renyi process, but would it be sort of substantially different if you scale, say, by any other? I mean, you keep track on polynomial many steps of this process?
Well, yeah, I mean, if you want to understand this process at time, say n to the 7, then I guess no exceptional event will kick in by that time. So I guess any sort of exceptional event, well, okay, it's not, it's more, I wouldn't, okay, so I certainly with this theory, I wouldn't be able, now I see a problem. So, okay, so let me be a little bit technical and tell you the problem. So I wanted to say that what you will have at time n to the 7, provided that this trajectory converges to a graphon. So there is something like, you know, value of infinity times n squared. And I wanted to say that these things will be the same, but that's not the case. So let me actually give you an example. If you start with a huge graph, an n-vertex graph and a single edge, okay? And your rule will be maybe sampling a quadruple, doesn't really matter. And if that's quadruple, if the sampled quadruple sees at least one edge, then you replace it with a K4. And if it's an empty set, then it remains an empty set. Then what this process will do at any time constant times n square, it will provide essentially an empty graphon. Whereas at time, you know, n to the 4, n to the 5, it will already be at the complete graph. So my trajectory, you know, the trajectory started from the empty graphon is a constant 0 in this case. Whereas already at a polynomial time, you will be able to escape it.
I see.
Yeah, so I don't think that this theory can tell you anything beyond times constant times n square.
Are there some other questions?
Yes, I have a question. Joel here.
Hi, Joel.
Okay, on your, I think this is kind of like your final question on your last slide. First, thank you, very interesting talk. Suppose you just look at the proportion of edges, that variable. Do you have non-constant, these periodic non-constant trajectories where the number of edges varies? Can it go up and then go down?
Yes.
Does your example allow for that?
Yes, that wouldn't be that difficult to construct. Yes, our example either already gives it, or if not, it could be easily modified to give it. Yes.
Okay. And then a second question, which may be close to your very last question. Could you get a trajectory where the proportion of edges gets arbitrarily close both to 1 and to 0?
That we cannot. So that's okay. So the reason for that is that we don't really have any examples other than the first 2 bullets on this slide.
Yeah.
So, or we have a little bit more, but this little bit more is really boring. If you find our periodic trajectory is stable or attracting. In other words, if you do start your graphon or with a graphon which is not on that periodic trajectory, but just a little bit away from it, then you eventually converge, you slowly converge to that cycle, to that periodic trajectory. But other than that, we don't have any examples.
Okay. Okay. Thank you.
Thanks for the question.